ser alguien en el 10, 12, 15. Sí, eso es más que...
Y entrenar todos los días casi.
Sí. Estudiar mucho. Un poco...
¿Es chino el Mqtt?
No. Es japonés.
Ah, ok.
Japonés, lo que pasa es que hay una vertiente brasileña. De los Gracie, exacto. Lo que pasa es que hay... al final es como todo muchas mezclas de influencia japonesa, del Wing Chun,
Ahora sí por la migración que hubo asiática, ¿no? En Sudamérica.
Bueno, no lo sé, pero también está mucho digamos, como un poco la leyenda de que en Brasil hubo una familia así muy... se llama lo que decía los Gracie, que son los que como hicieron un revamp de todo esto y lo llamaron Brazilian Jiu-Jitsu. Y con ellos, pues como se ha vuelto a popularizar ahora también, ahora Estados Unidos está muy fuerte, y en todo el mundo está como muy a tope. Okay. So hello everyone. Let's start. Let me go to... So first of all, questions, doubts, things from yesterday. Do you know what you have to do for this week?
Yeah, the group assignment, I don't understand what you have to do.
Okay, let me see.
I think the one from me.
Okay, let me see. Input devices.
Like the assignment, the global assignment was to censor something using like a micro made by us, and then like the group assignment or...
Wait a second. Oh, why doesn't this work?
Probe and input devices, analog levels, and input signals. So literally just measure now and see the difference and compare.
Yeah, I think this. So there are different ways to do this, and maybe I can show you how to do some. So either you use a multimeter for probing directly on top of the sensor or the output directly using a multimeter, or you can also use So I can show you how to use this. This allows us to measure, well, I'm sure that at some point you have seen something like this in your life. Let me bring that down.
Before you go more into detail, my question was to be like really simple. I understood that on one device, one sensor, you have to use analog and digital connection.
Yeah.
You have to take one analog sensor and one.
No, well, yeah, something like that. But also, yeah, so because this is something that we don't talk that much about. think it's interesting. Yes, put this. I'm not gonna show this right now, but just want you to. I don't. Okay. Now you see that I have. So the idea was either you probe something digital or analog. If you want to probe something analog, you don't need anything too complex because you just measure with a multimeter and that's it. But if you want to probe something digital, a digital sensor like just ones and zeros, switch or not, again, it's the same, it's just an even simpler solution. But if you want to probe something digital, as in a digital sensor, for instance, something that is communicating with you via I2c or whatever, that is not the scope, but you can do it too. You can either use this, which will show you the traces in here, or if you want.
What's the name of this?
That's an oscilloscope.
Okay.
Or if you want, this same thing, and I encourage you to try. This is the same but smaller, digital, and it's an open hardware version. And the super advanced one, which is a logic analyzer, which is, so these two are the same. And you see at very high speed what is happening. It can be an analog signal, a digital signal, so an analog value, a digital high or low, or it can be a digital signal as like very fast signal with ones and zeros, and you can analyze what, I don't know, I2c, etc., etc. This is what we call logic analyzer, or some people call it bus pirate, which is basically the same, but is meant for super high speed and to go then in here. And you can, like, this is like this, but with an extra software in here that also gives you some possibilities to know whether or not you are connecting to is I2c, is SPI, is etc., etc., etc. This, I think this is a little bit more advanced, and we can do it in networking if you want to have a look. And we can have a session in which we use it and understand what's happening when we send messages in Ethernet, in I2c, we see the voltage levels, etc. And this one, or the multimeter is the, like, multimeter, this or this will be like high level, like more and more complex. So the multimeter would be the simpler. Multimeter will be the simpler, and then this is more complex, and I can show you how to use it if you're interested. It's not very complicated, and it's almost intuitive, but I can show you the tweaks for this thing. Okay, and that's the idea. Doesn't have any more complexity than that. Okay, and regarding the individual assignment, it's just like use a sensor. Can be a sensor that you so that you can design the sensor and put it on the board, or you can take a sensor and put it on a board that you designed. So, but it cannot be a breakout board of the mini ones that we give you. You have to design something, a PCB at least. Now is the moment that I recommend that you more or less, since we're already in April, is that whatever you're gonna do for final project starts coming in. Because at this moment, you more or less will have an input, an output, several inputs, some outputs, and the board that you designed this week could already be thought for the final project. It can be a mini board that only has inputs, or it could be part of the bigger board with a microcontroller, with an output, etc. The output, for now, it could be just 3 paths to which later on you connect something, or it could be more complex. But the idea is that more or less you start mapping mentally what this is going to fit in the final project, because just this, you already know how to make a board, and you already know how, like, a sensor is super simple. So this is like a extra easy week somehow. Yeah.
What little board do we have?
So we have these tiny boards like these ones. This well, these small Arduino kits. So you just have to show everything to cameras like this thing. So you have, I don't know, microphone, temperature sensor, another mic. This is an infrared, whatever, you know. So all these things.
And this we receive them as a pub or what?
No, you can use this if you want, but you cannot. This cannot be your assignment.
No, we still.
So you have to design this actually.
Okay.
And put the components.
And we have the components separated somewhere, like the LED, the infrared.
Yeah. Exactly. Or, for instance, this board, this is just a temperature sensor. You could make a board to which you connect it. And if there's anything extra, for instance, this is a 5-volt sensor, and you have an ESP32, then you put the voltage divider. Okay. This is an analog sensor that whatever it needs, imagine it needs external power, etc. That's why I'm saying that making this for this week is nothing. But these have these things because they have potentiometers and a little bit more advanced things. But what you're going to do is so tiny that it makes sense for you to start integrating it into the final project.
Absolutely.
Okay.
Like a diagram for what we want to sense, like the one we did before. And
Yeah, I think so. Well, depend on your variables, but depending on like what your object is going to do. If you just want to sense something, you don't need it much. But if you want to like have an architecture of your system, then it starts making sense to start making some sort of diagrams.
Okay.
Yeah. Okay. What is that? Okay. So this system, this Grove, this is a C Studio manufacturer. And Grove is the system that they made with this standard method. You see that this is just a hub, and maybe I don't know this is some, but like Arduino and several things, right? And if you look, it's the same connector that we have here. So we know very well this because all these little sensors, we use them, well, some of them, we have used them for development. And if you want, of course, you can certainly use it. That's like 16 sensors. For the group assignment, we can just program. Yeah.
So technically, this is just to connect.
So that's a hub, yeah. Or maybe we can show it into the camera. No. So this is what we're talking about. It's like a hub for different sensors and has like a main Arduino and then some. These are all just the same that connect.
It's saying that the microphone is not.
Don't worry, I'm using this one. And then these connect to the different sensors over there. Okay. And this is just the Grove. It's quite cool, this thing. Okay. So it works.
C Studio, technically, they type of open source boards kind of thing.
Yeah. So Seed Studio is two things. It's a manufacturer. Well, it's mainly a manufacturer, a PCB manufacturer, but they also have a retail shop, and they sell their PCBs, and also they manufacture for other people. For instance, for us, we have an agreement with them, and if you can find the Smart Citizen Kit online in their website, they manufacture it and they sell it, and they also send some to us so that we make projects with it and stuff.
So that's kind of like the only thing that is done, that is not done in the Fab Lab, no, from the smart cities, because the rest
exactly.
of it is made.
Mostly, yeah. And there are some things that we outsource, like sometimes we cannot use all 3D printers or all CNC or the CNC, so we send them to a CNC. But the idea is that the whole system, except the electronics, of course, should be replicable in a Fab Lab, let's say. So that's why sometimes some things don't look as finalized, but the principle is that you can make it anywhere else.
Question,
Mhm.
sorry. For the individual assignment, if we decide to do our boards, if my final project board is going to be a Arduino that I'm going to add shields to, should I mill it, or I can use the base that has been manufactured for the Arduino?
For this week,
Yeah.
sorry. So for this week in particular, you have to make your own PCB.
Okay.
That you have to design it and manufacture it.
Okay, cool.
That PCB can have many things, not only inputs and outputs, and also a microcontroller. And so if you think well, or if you think it through a little bit, this week, input, output, and networking, it doesn't have to be one board for each week. It could be one common board. So you decide this week, you can explore different things and don't design something super complex. And when you get to output or networking, you make one PCB that has everything, and you killed all 3 assignments. That's up to you, So it's more or less.
Start from now.
Or you can start from now, but you don't know some things from networking, which will change in the future. But we can give you advice on that. If you have more or less something clear for the final project, it makes sense because you kill 3 in 1.
So maybe we don't build anything this week. We just prepare everything, start planning, and on the networking week we give the PCB.
You could do that, yeah. Or you could start prepping also networking in this week a little bit.
By reading the documentation.
And by talking to us so that we can give you, okay, I would use this type of protocol here, I would do this, whatever, and then you decide. And also this week, use it to explore different things on inputs. Like normally, we only tend to use 1 or 2 per project, but it would be nice to have, I don't know, analog sensors, digital sensors, play with different formats, like sensors that are very far away from my PCB, sensors that are connected to my PCB. If I draw a cable from here to the other side of the room and I have an analog sensor, does it work? Doesn't work? These type of things that we don't ever experiment and we always ask. It's interesting because at the end, from here to here, it could be the cabling of the machine. Yeah, this type of things. Yeah. So yeah, more question?
What does PCB mean?
PCB is a printed circuit board. Is one of these electronic boards.
Yeah, the ones that was showing the diagram for all the sensors. She showed like
so
an image and then he did like a video.
So it's exactly. So it's what we have designed during this week here. Which let me show you.
It's like the one. Is it made of copper, no? Or what is it?
It is copper, yeah. So the PCB has it depends, but it has a base of phenolic resin, different types, FR4, FR1.6, FR whatever, and then there's copper. And there can be many layers of copper. Normally, it's either 1 or 2. So it's resin, copper, a little bit more of resin, a silk screen for like painting things and putting letters, and the same on the other side. You can communicate both sides with vias, which are copper cylinders that just like a lift, communicate one layer with another, and you can have up to, I don't know, I think I've never done more than 2. The Smart Citizen has 4 layers, and there I think it's up to 64 layers. Wow. That's what I think there is. I know that with KiCad you can do 32 layers, but that is like, I mean, 32 layers is like.
those computers that have this kind of number of layers? Or maybe
I have no idea. Honestly, I never probably. Yeah, I don't know. But you can see on the side on the thickness of the PCB, you see also that there's like that it comes a little bit apart if you break it.
Yeah.
And I don't know if those are not the layers exactly, but the more layers they have, the less consistent the resin is, and then the more it comes apart. So a PCB that is going to be manipulated by people, etc., more than 4 layers or 8 layers is like too complex. Yeah. Okay. So, any more things? Questions? So the idea for yesterday's class was to just have an overview of different sensors. Today we're going to talk about 2 more things. One is an introduction to different setups for the sensors, which how do we deploy a sensor and what things do we have to consider regarding power, regarding communication, the thing that I call the heavy lifting, who does the heavy lifting in terms of energy, power, communication with different computers, etc. And then I'm going to give a very, very tiny introduction to DSP or data analysis. DSP is digital signal processing and is mostly in the past like 3-4 years what I've been doing here for the sensors in the Citizen kit. I will give you very brief notes because it's a little bit like heavy, but the documentation is here and I'm more than happy to give you a lot of material. I'll give you a lot of references in Python and in Arduino so that you can make use of the signals in a smarter way, okay? So if there's no comment, I can, yeah. So what we were talking about yesterday is that we have a sensor that is giving us information and we have to interface it with one computer. That computer can be an Arduino, can be the microcontroller, the board that you design, and can be something more complex like an actual computer or a Raspberry Pi. Important questions to ask when you do this. How do we read the sensor? Is it digital or analog sensor? Can we read it? Does for instance, the computer has ABCs? Does it not? What are the voltage levels, etc.? And in an actual sensor, like a more advanced sensor, are there libraries for it? Do we have possibilities to get a library from Adafruit, from someone else, to see if there's something that facilitates a little bit the process? If sometimes it's just going to be an analog read, but sometimes it's going to be a sensor library that implements many things. And normally digital sensors will need of a library like that.
Can you give an example of
a digital sensor?
No, yeah, a digital sensor that might need when we say library, what do we?
Yeah. So for instance, a temperature sensor can be as simple as that one here. This one. This is DHT11, and it's just
what's the name again?
DHT11, and it's an analog sensor at 5 volts. The same manufacturer, but in a more advanced setup. That's this one that I'm showing there, SHT31, that I know very well because it's the one that we put in there.
Okay.
That probably you also have in that board. I'm not sure. Let's see. That's temperature is HT22. No, there's not. It's not here. But okay, this is the big value of that one. So this is a little bit more accurate, but it's more or less the same.
Those ones they communicate analog.
Yeah. The other one is a digital sensor, and a digital sensor means that
the
SHT31.
Is the digital one, no?
Yeah.
Okay.
This one. These ones. What would you guess that is more accurate?
This one.
Yeah,
Oh no.
You sure? Than this one?
I'm not sure. No.
So this is way more accurate than that one, because this inside has a small microchip inside of it. It's much smaller, and the materials which is made and being much tinier in the mass that it has less inertia, can read much faster. For this to stabilize, you need 5-10 seconds. For this to stabilize, you need half a second or 50 milliseconds. Okay.
Yeah.
So this is really fast.
Okay.
The interface is, for instance, the one that. So this is I2c interface. It's very common interface. We'll talk about it, but basically just gets 5 volts on ground and 2 lines of data. One is the clock and one is the data line. And in this case, we just communicate with this cable, well, with this Grove system. For instance, for this, if we go to GitHub, normally I would do Adafruit. Adafruit, they have really good libraries for all these things. You can connect this sensor directly to an Arduino via I2c protocol and use this library. They also have one in Python for a Raspberry Pi. This is the same sensor, but a different layout. And with this library here, an Arduino file, include SHT31, begin in the address. The address is a numerical number for devices in the I2c bus. So in the I2c I2c is the same. You can hang, it's like a bus, like in the can, in a car, and you can hang a lot of things that are interfaced with an address. It's like computers on a network on the internet, the same thing with sensors on this thing. And you can put a lot of them connected, and they need an address. And this address, in this case, is 44. And then
Can you like locate it technically also?
No, normally they're defined by hardware. Well, they are per device. There are up to 16 times 2, 256 addresses. And normally most devices have 2 addresses. For instance, this one has 43 and 44. And in some of them, you can tweak them with a jumper or something. Okay. Like you solder a jumper and then they give you a different address, so that they don't collapse, let's say. And basically here, this object SHT31 read temperature. Okay, that's an example of using a library. The rest is just it doesn't need anything. But here you just begin the sensor and read it. That's it. And that's the power of the library. You don't have to interface with anything else.
Okay, so technically the library allows us to communicate with the
exactly.
With the thing.
Yeah, exactly. This example, if I take it and I clean it up, this will be just.
And then after that, you start adding your code, like
your actual
what you want him to do.
Exactly. So if I want to clean it all up, this is how it looks. Actually, not even like that. And if you are using the Arduino IDE, just so with this, you can read already a high-end, quote unquote, temperature sensor. And this is just for serial print, so not even. This is the library object. So this is the definition, the object, begin, read temperature, read humidity, and then you put the rest of the code here.
Cool.
Yeah, and that simplifies a lot. Behind this, there's a huge amount of code that talks with the sensor, interfaces with the different buses, whatever, and gives you the final value with just one line of code.
Cool. Just can you explain the syntax of the line SHT31 space SHT31 or something?
Yeah.
Can you explain the syntax?
Yeah. So this here is the type. This is the same as if I did int. or float. The first item here is the type. This here is the name of the object. This could be value, and then equal to something. This equal is in what we call object-oriented programming. This is the class definition of this type of object. And basically, this object here is defined as class, class name, and then the different functions and properties that that object has.
Is there a classic way to find which class you have to use in the library, or like for this kind of control, or it's every library will depend?
It will depend, and normally a good library would have examples. Yeah. Normally, well, you could do that, but if the library that someone makes and puts it on GitHub doesn't have example, no one is going to use it, because you have to dig into the code and it's kind of complicated. Sometimes in here you can give also some arguments, like, I don't know, imagine that we could initialize with the address as well already. You could do this and not pass it in here. That would be another way of doing it. But in this one, it's not the case, but there could be arguments passed. Yeah.
And can you repeat, please, what is the Adafruit underscore a? Yes.
This part?
This
is
the second one after the value.
Yeah. So this is the type.
Okay.
Sorry, is the class. So you, in object-oriented programming, you have classes, which are different types of objects that you can declare many times, but that they all share a set of properties.
Okay.
That can be variables inside. For instance, I could define a class that is tables, and tables can have 4 legs, 5 legs, certain color, surface, height, whatever. No, I could define another one that is chairs, and etc., etc., etc. This is the object, or this is the format in which we declare an object of that class. This is the class.
Okay.
And this is the name of the object that we're making.
Okay.
So that class then is referring to the Adafruit.
Exactly. If we go into here, into this Adafruit blah blah .h, this is the header file in the library that is here. Yeah. When we say include sht31.h, we are including this file. Yeah. And when we include this file, there's all these definitions that is blah blah blah, and then the class. See here, class, and then this name. And it has all these properties: begin, read temperature, read humidity. That is the methods that we call to get the different things. And why do we put this one here? Because in C++, when you declare an object, you have to assign a type to that object. The type is either int, boolean, float, etc. And the classes sht31 return a type that is sht31. So normally this name and this name are going to be the same when you declare, when you make a class.
The type is defined in the library.
The type, no, the type is just a way for, it's a little bit unnecessary in a more high level language, but the type is assigning what are the allocations in memory that you would need for that object. So for instance, a float needs 64 bits, a boolean needs 1 bit, an int needs, depending on architecture, 8 bits. So when you say int, the compiler is saying for this variable, store this amount of space, because I'm going to use that space for this variable. For this other one, store this other amount. And when you compile, this gets assessed and defines, among other things, this type of stuff.
Well, no, but just one question. So technically, if you go back to this, but in this case, it's not written either int, neither float, neither nada. You
Exactly.
just wrote it, no?
Yeah,
So
no,
it's
exactly.
just that.
It was just that, but I just put here the example. Imagine that this was like int 8, and here
So then, where is the fact that I was for SHT31?
Yeah.
Yeah. So is not defined in here. Is defined. Let me see. Here. So this is the header file that contains what we call headers, which is these type of definitions, overall definitions of the code, etc. And here is where we declare the definition of the class, but just like the main items, it's like the summary of the class. Like if we had a table of contents of a document, the same. And in here is with where we declare the actual class, the actual object, and this is the type. And this is, but normally good people put this name the same as the type.
Okay.
Normally, like people that do these things properly, they normally put the same name so you don't have to dig into it.
For the library, the H, it also imports the C++.
Yeah, so when you import this, that it all goes in cascade. Let's say one imports another and another and another. Yeah. Yeah. Okay, so ¿dónde? No, antes había uno de que no detectaba el micrófono. Tranquilo. Okay, so important things there. If we have an Arduino or a small computer, can the computer read it and interface with it? Do we read the sensor? Is an analog or digital sensor? And do we have libraries for it? Then it becomes to the point of, do we need another computer or not? For instance, do we need a laptop to talk to the Arduino because we want to store data, for instance, and we want to send the data from the Arduino to the laptop and store it and then analyze it? Or do we need post-processing? Imagine that we're running algorithms in our analysis of the data that we cannot run in the microcontroller itself and that we need another computer. For instance, a big server or something like that. How do we communicate between them? Do they communicate with wire? Do we communicate with Wi-Fi? Can they communicate with wire as well? For instance, do we have one of those robots that you built? If we have a wire and we want them to fight over there, can that happen? Or do we want to put a battery on them so that we don't have to put a cable to power them? Is that okay? So this is more or less some concepts just to keep in mind. It's not going to define anything for the week, but for the following ones, it's important that you go through this checkup. So for this checklist and see how is my actual project? Do I need wires or not? Because at the end, it happens that imagine that you wanted to make a drone and you don't have way to communicate with it. Or you want to, and the chip that you put in there that cannot talk to the sensor. Then you need two computers on the drone. Then the drone has a lot of weight and then it doesn't fly. Yeah, so this type of things. Oh, am I not sharing the screen?
I don't know.
I should, no? Shit.
You were sharing before, so just have to.
Oh. Okay. So, what else? Things to consider regarding when we interface with the sensor. There are three frequencies that we have to consider. Frequencies, understanding how fast things happen. Okay. First thing is that the frequency at which the sensor gives us the data, meaning does the sensor can give us the data really, really fast. For instance, a digital sensor will give us data at 10 milliseconds, 1 millisecond, 5 milliseconds. Perfect. We can read really fast. The frequency at which we can read the data. For instance, can we read the data every 5 seconds, every second, every 50 milliseconds, depending on the speed of our microcontroller, which is normally not going to be a problem, but probably is going to be a matter of our microcontroller is doing other things. Like we do something, we take a reading. We do something, we take a reading. And that something takes 1 minute. Then we can only read the data every minute. We cannot read it faster, right? So maybe we don't need a sensor that gives us data super fast. Maybe we can, with one sensor that gives us slow data, it's okay. And finally, there's something called what we call natural frequencies of a system, which is, imagine a system, for instance, imagine the temperature of this building. We can imagine that the temperature will be something on a daily basis that is going to be something like this. Imagine, so this is when we arrive in the morning, increases because we turn the heater on, there's sun, etc. Then it cools down, goes back up, cools down, goes back up, etc. Right? So this is the temperature of this room, for instance, and we want to know what the temperature is. So we want to measure that. The natural frequency of this temperature is basically the period at which things repeat. So every day happens the same thing. And we have to take that into account because imagine that we were taking samples only here at this point. We take one sample a day, and that sample is exactly when the sun is at the highest. And we say, no, we have to dimension the cooling system for the building based on these readings. Then we have all these that we're paying for extra because we only sampled when the sun was at the top. When things get less, let's say, with less inertia, like a building has a lot of inertia, but for instance, imagine that you are monitoring an encoder of a motor that has these times, but 1,000 times per second, or the temperature of a 3D printer, or the temperature of a machine that you design, or anything else. There can be frequencies in the system that oscillate, things that oscillate in the system that give you sometimes one data and sometimes another. And at least you want to be able to sample at least twice as fast as the natural frequency of the system. So imagine that we want to sample the temperature of this room. If we sample at least once, then I'm only going to capture an average measurement, either here, here, here. That is going to be not the good one. If I sample 2 times, at least here and here, I'm going to get some data, or maybe here and here and here, which gives me a little bit more of information. Then I would imagine that the temperature is either like this, but it's not like that. If I sample one more time, then I have, for instance, something like here, I have something like here, and I have something like here. And this already resembles a little bit what I actually want to capture, okay? So the more times, the faster that I sample, the more accurate my signal is going to be, but sometimes I don't need that. But for this, you have these 2 limits. The speed of the sensor, or these 3 limits, the speed of the sensor, the speed of your system or microcontroller, and everything that is doing, and the speed of what you're monitoring. That sometimes it might be super fast, or sometimes might be super slow, okay?
What's the key takeaways? Like,
Yeah, so it says, we don't need to sample faster than the sensor gives us data, of course, because otherwise we just get repeated values.
Mm-hmm.
And we need to sample at least as fast as the Nyquist frequency. Nyquist frequency is a theorem in sample or DSP that states what I just told you, that at least, so the natural frequency of the system, considering that is the natural frequency at which things start to repeat, like because things oscillate and they start to repeat in a periodic way. So that's the natural frequency in the system. Nyquist frequency is double that. So, and frequency make double the frequency means sample faster. So you sample more times in that.
Okay.
This is a little bit more like DSP type of things, but in some things you might need them. Okay.
Okay.
For instance, motors, servos need a lot of speed. If you have, you'll see that some microcontrollers cannot interface with servos because they are slow. The microcontroller is slow enough and cannot sample the potentiometers to be able to adjust. And then the servo otherwise starts like vibrating because it's getting here to this point and it says, oh, I'm up. Then gets to the point back, and in the middle it didn't take a sample. So it's all the time like pam, 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 pam. And it doesn't know when it crossed the 0 or anything, and then it never stabilizes. Okay. More things. Oh, what happened? Ah. Well, if you want to read it, it's an interesting read in Wikipedia. So some setups here. Sensor, first one, we connect a sensor to an Arduino and maybe we connect it to a laptop. Arduino, consider it the board that you design, or directly this could be the whole PCB, etc. But the idea is that you have something like an Arduino and maybe you connect it via USB to a laptop. You have a sensor and a Raspberry Pi, which is not going to be in most of your cases, but you could do that. You could do a sensor to an ESP32 and then data over Wi-Fi to a laptop. And this is in case that you have cameras. If you want inside some cameras and things like this, we can also talk about them, but it's not for this week. It will be more for the end.
Wi-Fi would be like using Bluetooth.
Wi-Fi, like network, like Wi-Fi, internet over the air.
So Bluetooth would be something different.
You could use also Bluetooth in the ESP32. Actually, I will replace this instead of Wi-Fi. It would be over the air communication, not cable, but over the air. Yeah. Because at the end, an ESP32 also has both Bluetooth and Wi-Fi, and your laptop very likely is going to have both as well. Yeah. So let's look at the first one then. The sensor. In the Arduino, we read the sensor with an analog read, normal and analog sensor. We have to start the communication on serial, because we are going to talk after with the computer. So we have the serial communication in the voice setup. And we read the sensor in the loop, and then we send that via USB. When we say serial print ln, we are sending it through the USB. USB is universal serial bus. So when we send something, it goes through the USB. And here we send it every 1,000 milliseconds, which is 1 second. You can change this depending on many things. Your assessment before, how fast things can be read, because this is going to affect how fast you read the sensor, and how much you can read on the laptop side, which the laptop normally is going to be really, really fast. It's not going to have any problem, but maybe you don't want so much data. Maybe you just want to measure every second because things don't change that fast normally. Depends, okay? Please.
No, go ahead. I asked about today.
So the time of the loop compared to the time of the delay. Like, how will it impact? Is it really long to run the loop or happening at 1 year?
No, is the loop normally, if in this case, so these three functions, we could time them, and we can print the CPU time before and after, and is the order of microseconds. So it's a millionth of a second or 1,000th of a millisecond.
For example, the delay here is 1 millisecond.
No, it's 1,000 milliseconds. 1 second.
1 second.
If it was 1 millisecond, so 1, still it would be faster.
So the 3 lines is 1, delay 1, or delay 0.000.
0001.
Okay.
Yeah.
So there's,
Also,
what did you say, sorry? What's the last thing you said?
so I understand what he said, that the equivalent of this 3 line is delay 0.001.
What
Yeah.
three
So
lines?
imagine these 3 lines,
these three
int,
lines.
float, and serial. If the time that it takes to execute them, we replace that with a delay, how much that delay would be. And I'm saying that it would be on the order of microseconds.
Okay.
So delay 0.001.
Okay.
Model.
So actually, if you remove delay 1000,
Things would be like,
it will just go as fast as it can.
exactly.
It will take the maximum.
Yeah.
There is no sensor which communicates at the speed.
Probably there is, but normally, no. I mean,
The phenomenon we analyze and everything.
yeah. Probably with some other sensors like the ones that we were showing yesterday, like a time of flight sensor or things like this, maybe. But as soon as you interact with the physical environment, which is either movement, light, temperature, physical phenomena, these things don't happen so fast. Yeah, a microcontroller goes much faster than the real world, let's say. But it can be that the sensor that you are interfacing with, instead of analog, has a microcontroller in it. And that microcontroller has buffering, has, I don't know, whatever, that is able to give you the data super fast. But it's very, very unlikely that that is going to be below even 20 milliseconds. For me, 20 milliseconds for reading a digital sensor is already like fast, as from my experience.
The 9600 bars, what is it?
Yeah, so serial communication needs, it is just 2 cables.
Yeah,
I explain these things because they are probably not the topic of the week, but
sorry.
no, but I explain them because I like that these things, we repeat them. So, you know, RX,
Okay, I got it.
RX, TX, TX, RX. So it only has, so they interchange because the receiving side is the transmitting on the other, etc. You already know that? Sorry? Yeah, it always happens. But then, as you can see here, there's no clock. So there's no way for both sides to know at which speed the other one is talking. So imagine that I send you a voice message on your phone, and I go like blah, 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 super fast. And then you try to listen, and you're like, what the fuck?
Yeah.
Unless I tell you the speed at which I sent you, and you're able to slow it down, then you will never understand it.
Yeah.
So this is the same.
Okay.
In this case, what we do in this type of protocol is that we tell both ends that you're going to talk at this speed. And to be just super explanatory about this is a unit called bots, or in Spanish, baudios. Baudios, it comes from a guy called Bod that was into the frequency domain, like a theoretical into the frequency domain. And basically what it means is that imagine that you have a signal that does this. That normally all digital signals are going to be like that, faster or slower, right? So a baud or 9600 bauds means that there's changes like this one or this one or this one.
The first change.
Yeah.
Okay.
Or can be up or down, but one of both, either a change.
It's a cycle.
It's a change in the signal. With the change can only be from 0 to 5 or 5 to 0 in a digital signal.
Okay.
But we agree on either one, and we say that you count how many changes are there per second, and that's bots.
Okay.
So in this case, we are talking at 9,600 changes per second.
Okay.
In the serial signal. You could go up to very high number, but not all the devices are able to accept that. mostly not because of the device itself, but because of the connections. Because if you use a cable that is not good, or doesn't make good contact, or that the solder is not good, or whatever, then the speed has to be reduced because the signals don't travel well.
And this is the communication between of data between the
These two.
sense.
Is
So
this communication?
the void loop is between the sensor and the Arduino and the.
No. So there's a little bit of both in them. This is serial. So
Okay.
this part is the USB, and is the communication between the Arduino and the laptop.
Okay.
And this part as well, well, actually only the part of serial here,
Okay.
this one is also that.
Okay. Everything that's serial is definitely that.
Yeah, and then this part, this one, is reading the sensor.
Okay.
Yeah.
Cool. Thanks.
There are standard 9,006.
Yeah, the communications in both are, I think, like based on 8 bits. So I think 9,600 would be something like 11.
Are these things you saw in embedded programming?
No.
Okay. Good.
Not all these things.
I didn't miss it. Okay. Cool.
I don't know exactly where they come from, but they are standard. So 9,600, 115200. These things, when you see them, you know that that's for sure a baud rate. Actually, it's called baud rate. And they are standard. Not all these things we saw. No way. Yeah. So this is, and this code goes in here in the Arduino. Okay. Things to keep in mind here. Okay, well, that basically what the purpose of this is that we want to read the sensor and send it over somewhere. Yeah, because we cannot do anything in the Arduino because we don't have space, because there's no, the processing capabilities it makes it impossible, or simply because we want to store the data in here. Yeah.
And usually, how does the result portray itself on the not portray itself? How do we see the data? How does it?
That's where we are going to. So there are two ways. Well, there are many ways, but basically you can open the serial port in many different fashions, right? One way is to use Arduino. The Arduino IDE already has, well, the serial monitor that you normally use, and a serial plotter that basically plots anything that comes in the serial through USB and puts it in a plot. So it's here.
I mean, the serial print
It's the same. It's the same. So it's the same. So anything that comes from in the USB that is a number, it will go into the plotter as well. So, but you can only have one open, I think. So the monitor, well, I cannot open anything because I don't have an Arduino connected, but the monitor is this window that you know, and then the plotter is a small graph that just shows, and it has to be a numerical value. Okay, so that's it. And at least you can put them separated by commas or tabs. So if you print a value and you put a tab or a comma, it will understand them and put them separate, but on the same line. So they have to be.
No, I didn't get that. Sorry.
Yeah, imagine in this example of the temperature that we say serial print ln T, and that we just print the temperature and we just have one trace.
Okay.
But if we want to do serial print ln H, in here I would do this, because this, okay, I see your faces. So this this does this will give me, if t is 5 and h is 3, it will be that. Okay?
Okay.
Because we have the ln. ln means put the temperature and then this. Another, which means carriage return, new line, right?
Yeah.
So this is ln. It prints
It puts it on another line.
it puts the next one goes into another line. Yeah. But this one,
It will
that's
give it like tak.
exactly will do because this one is ln, so it will be like that. What can you do to put a space or a comma or a tab? Then serial print space,
Which means nothing.
which is just, it would be like this, or you could put something like that, and then it would put something like this.
Just a question, why did you keep the ln for the h?
So that when I come back next on the next print, I already start on a new line. Yeah.
By line you mean vertical line?
Yes.
Okay.
Yeah, a row, let's say. So
No, okay, like this or like this?
so I write like t comma h and then go here t comma h, and then there's the ln is t comma h ln t comma h ln t comma, yeah.
Cool.
Okay. So with this you can have as many values as you want. You can just put as many rows as you like, and then you can just plot them in here and see them. Another way to do this is to here is to do it with Python if you like. And for this you need to, for those that are like that like Python, you can use PySerial. It's basically just a module that interfaces with USB or the serial communication. And with this example, you just say import serial, import the port name, which is the same port name as the one in Arduino here, this one, or the ports that appear in here. Yeah, those either, I mean, the actual one of the Arduino, the same name. You put it in here, and then the speed, the same speed that we put on the other side, 9,600. Yeah, the same number.
The bots, yeah.
The baud rate, yeah. You see, same on both sides. And then forever, so while true is forever, repeat until the end of the script, read the line and print it. Then you could also plot it, you could put it onto a CSV file, you could, I don't know, put it in a database, etc., etc. And this is a simple, just to get the data and then do whatever you want with it. Yeah.
Every time you want to access Python, you need to put the pip search piece, serial piece, whatever. That's the
No,
first thing.
no, this is in the term, it's only to install. Yeah.
If we have it already, we just go to Python and we go.
Exactly. Yeah.
Yeah. And if we don't want it forever, like if you want to do it for like 3 hours, for example, I'm saying whatever. But like,
yeah. So here you can either have a counter and do it forever, but whenever you reach, sorry. So while no. So you could say what time now equal time now. I think it's this. I'm not sure, but basically this gives us what time is it at this very moment.
okay.
And then we say while true, and then we do our thing with the sensor and everything, and then we say if time.now minus time now larger than 3 hours, break.
Love it. Okay.
And then you just get out of the while true and do something else.
Minus time underscore now is technically it's
the beginning.
It's now. It's technically the moment that is passing.
So this one that actually time start
is the moment you're coding this.
Exactly, the moment at which you started this script.
Cool.
And then this time.time.now is the actual timestamp of this very
the moment
moment.
that's passing. Okay.
Exactly. So next time I will be here and I will subtract to when I started. If that's more than 3 hours, I stop. If not, next one. Check again. No, check again. No, check again. So that's a way to do it.
And sorry. Okay.
No.
And how come in Python you don't say at which frequency of time you want the value to be read?
You can do that actually, and that is something.
You know what I mean?
Yeah.
In Arduino,
So here, this library, that's not a bad question actually. So you have the serial port and the drivers in your computer are a little bit more complex than the ones in the Arduino.
Okay.
And this has a buffer, a small buffer that stores some data in it. So you receive, and basically everything that you receive is stored in a buffer until it overflows, but the buffer is big enough. When you read the first value and read it again.
Okay.
If you read it fast enough and you don't have anything, it will give you an exception. It will tell you there's nothing to read.
Okay.
So normally you say, if there's nothing to read, because they are sending me data slower than I am reading it, and there's nothing, then you say serial.available basically means that is there anything, and then I read.
Okay.
And if there's nothing, I don't read.
So this also goes as fast as the computer can go, as long as there's no changes, it wouldn't show it.
Yeah. Yeah.
But you can ask for the changes.
So you ask for the last line.
Okay. Yeah.
For the first line actually.
But what will appear is at the frequency that this can
read.
Okay, cool.
Yeah. And that might be and will be very likely much faster than the other one.
Which might be counter. I mean, we can limit it though, because if it's counterproductive.
You can also either delay it in here, just put another delay, or basically you can say just leave the reading, like the responsibility for that one, and then here you just say whenever there's something, read it.
Okay.
If there's nothing, ignore it. Okay. Yeah, and don't ask for anything. Yeah. If you want more about this example, you go to the Code Club. That this year we are doing less of these things because we're with the project of the Pi, just for changing, but everything is in here in 2020, Python and hardware, and you can get the whole setup for this. With Python, an explanation for many more things, how to interact with it. Actually, well, this is Python too, but you can adapt it some things just with the parentheses in here. And this is the full example all explained, okay, with all the instructions to interact with it, okay? What else?
Did you say that Python is like easier than Arduino? Or
no, it depends. It depends. Yeah, it depends. I mean, Python for me is easier now because I've done it for a long time. But the thing is, Python is meant to be easy. Let's say if you read Python here, you say, well, this is not actually Python, but if you read a Python script, it's very, if you actually read it, is if time larger than X, blah, blah, blah. It has some things, but it doesn't have all these parentheses, all these weird brackets, double, semicolon, and whatever else. And it makes it really easy to read. And for me, I mean, it's meant to be easy somehow, which makes it easy.
Okay, so it is.
Yeah, for me it is, but also, but the normal workflow, for people to get into programming is through Arduino now.
Yeah.
Like not many people start doing Python, like people that is not like in tech or anything. Yeah. They normally start with Arduino, and then they go more complex, and they see Python as like, ooh, but it's not. And normally, I even started that way. I started doing in Arduino, simple things. And then I went into Python, and at the beginning I was like, Python, that's bullshit. And now it's like, I even have packages published and things like that. So it's a matter of perspective. Okay, so, well, here some notes about environments in Python and things like that. We talked about it in the code club. It's not very important, but just in case, if you want to use Python, here are some notes, and also in the code club as well. There's here in this link, there's more information about how to set up an environment in Python. This is if you want to use it with a Raspberry Pi. There's some notes. If you want to use, for instance, a digital sensor in a Raspberry Pi, the commands that you have to run and the things to enable the I2c bus, to detect devices on the bus, and then a Python script. Well, this is the pinout, and then a Python script to read the same sensor that we saw before in Arduino, but with a Pi, yeah, using Python. So this just has the digital sensor and a Raspberry Pi. Here is the setup is much simpler, but it's not what you can do this week. But still, if in the final project you want to use a Raspberry Pi with a digital sensor, you can, and you can use Python for it. And this is the example, okay? This is for cameras. That is a little bit out of scope. I'll leave it. If you want, I can talk a little bit about this at the end, but it's clearly out of scope for today. We can do on a code club, sorry. And then another example. Imagine that you have your sensor, you have an ESP32 or Raspberry Pi, and then you want to send the data over Wi-Fi using Wi-Fi to another laptop or to a Raspberry Pi or to another ESP32 that you have somewhere else. So you could use something that is streaming, like on a streamer, let's say, the Raspberry Pi and the sensor, and then talking through Wi-Fi and send it to another place. Yeah. So you can do this also with cameras, and the idea is that let me see the example. Wait, I don't have this example here, but I'll show you. I'll put the example. Sorry, I didn't realize it was not there. Okay. Yeah, okay. So we'll see more about this on networking, but basically using ESP8266 or ESP32, you can connect to a Wi-Fi network, read a sensor, and then send that over. You can send that over using many protocols. Normally here we like one called Mqtt. We'll talk about it, but basically it's a protocol that can connect in a broker, like a central server. Things can get published and people can read them. And each person or each device has a name and sends things to a topic as if it was in a chat room. Let's say, as if we were in Telegram and Telegram server. I talk to Adrian today, then to Lynn, then we make a group, then you listen to our group, and etc. So the same, but with sensor data and devices.
What you use for smart city?
Yeah, exactly. Then we have in the kit we have that antenna that sends data over Wi-Fi using this protocol to a server and sends it in this using MQTT. The thing here, as an example, and not too very complex, is that you can read a sensor every whatever while that you want, and then you can publish the message to a server. All the rest, this is just debugging. Well, no, this is not debugging, this part not. But all the rest is just to connect to the server and to connect to the Wi-Fi network, and it shouldn't in principle be touched. But basically, if you take this and use a ESP32 and send the data over and connect on the other end, you should be able to receive it, and you can communicate, and in principle, you should be able to do that in the networking week. Yep.
Okay, not now.
But in principle, these examples are already here, and I want you to more or less have this mindset that my board doesn't have to be all in the same. I can put something here or there, and this is that very tiny with a small antenna, and I have my laptop, or I have a Raspberry Pi, or I have another board, etc., etc. Okay. So that's for that setup, and I'll put the example in there. And for this, that's it. Here, just a small clarification. Here, when we talk about networking, we'll here talk about this. This is the broker, let's say, like the chat room. And these are the messages being sent, like temperature, humidity, whatever. And these are people subscribing. Okay. It can be anything, what you're sending here. Before we go into the very last part, do you have any question? Okay. So very, very last thing. I don't really want to take that much longer because I know it's heavy. Let's talk, well, actually, let's take 5 minutes break and we talk about DSP. Okay. Yeah?
Yes.
Esta tarde me voy a las 4:30, que voy a hacer un episodio de ello. Pero, pues mañana, o mañana. Pues, si quieres mañana por la mañana, así preparo bien las preguntas. Pues mañana por la mañana, si quieres, por mi perfecto. Si estará hoy. Hoy no, hoy justo me voy a las 5, tengo que estar viendo una cosa. ¿Hasta las 4:30? Sí, pero no sé cómo es que creo que tengo cosas por la tarde, no sé si voy a estar muy disponible. Si puedes mañana, mejor, a ver, me liberan.
Mañana
estaré por aquí.
Más o menos.
Sí.
Este me gustó mucho, lo compré porque intentamos utilizar este un día con ese del verde, pero es que era un poco complicado. Y este te viene, yo creo que pague 20 euros y está funciona súper bien. Sí, claro. Te viene con eso y eso creo que lo compra aparte para entender un poco qué es más genial. Y es muy sencillo, ¿no? Pero está bastante bien. Bueno, pues lo puedes usar esto para... Lo utilicé para divulgar los juegos y una pregunta que con eso, o los demás podemos divulgar el pero ¿cómo puedes ver lo que pasa? Porque las mensajes si son largos, si uno... No, esperas la señal, pero no sabes lo que pasa. Con el Logic Analyzer, sí puedes saber lo que pasa. Entonces, esto es I2c. Vale. Entonces intenta ver packet headers y para saber, pero con esto no solo ves no hay forma de y no, lo recomiendo porque no es muy caro y bueno, permite hacer cosas de nuestro nivel. Porque es que, ¿cuánto vale el verde? Esto no lo sé, la verdad. Lo compró Edu. Porque parece bastante guay y todo. Igual es.
C'est un oscilloscope.
Ouais.
D'accord. Tu l'as utilisé pour le.
Saps quan la Feren diu allò de circle differs net des de start point o algo? Que és
But should we book
el
an hour for you to work?
l'arc fitting este en advanced parameters.
Mira, no recuerdo, pero vengan los que es una amiga.
Do I need to book an hour? To,
Well,
or
maybe
if you're
if we can set up
my
a
final project.
Cambio la estrategia.
No, I would say that we, especially because we have like minutes of planning, it's like, yeah.
Okay, okay.
So I need to know more or less. Like, so I can plan my day. But if you want, it's something somehow short, but all we need to do that. Just, you don't know, you can send me an email as you're around, so that, but you see that sometimes now. Like last year, I was way more available than this
Yeah,
year.
I was literally telling Edu, like, you're not very much around.
Yeah, I'm in the lab, but I'm always upstairs.
Okay.
No,
Because you have like more work on the smart citizen.
Yeah.
What, you got like a fund or something?
Well, this one commercial.
Oh, okay, nice.
We're selling a lot of sensors.
Nice.
Which is good, but also means a lot of work, and we don't have many people yet. So
Yeah.
the team is very small. And Victor is also very busy. We try to have some freelancing, but we are in this moment of, okay, we sell. We know that we're selling, but is it like there's some passion right now? Or is it because there's a lot of funding for sensors? Or is it because we're good? And we don't know if it's going to sustain. And then if you hire someone, then you don't know if you can have the money or not. So it's like always this thing. But we hope, and we think that it's going to be okay. Like we're going to have like enough for the following years. And we're looking into that, but it's not there yet. So
yeah, it's always the same the first 2 years. I don't know how long you've been on it for more than 2 years.
Yeah.
But since you went commercial, it's last year now.
Yeah, exactly. Yeah. So last 2 years, we actually were commercial 1.5 years actually, but before it was also all European funding. And now we have some, not so much, but at least, let's say the core activities can be kept with European funding. But then if you want to grow, it's very difficult unless that you risk a little bit onto selling, either sell more or I don't know. So is that impasse. I'm gonna go use the bathroom very quickly.
It was literally measuring signals with the oscilloscope, no? The group assignment is measuring the signals with the oscilloscope and the multimeter, you know?
All multimeters.
Only, no, oscilloscope for the digital and the multimeter for the analog.
I don't know, so to measure with, maybe we could measure with Arduino also. I don't think there's any correlation. Even what I did when I was working with my Raspberry Pi, I created a diagram in the terminal. Like, you measure from 0 to 5 volts. So I was saying, if you measure 0.1 volt, put 8 here. If 0.2, put 8 here. If you measure 5 at the end. And so in the terminal, you could see the line and the just with letters or characters being drawn on the screen.
That's
So I
good.
think whatever interesting way to read the signal we find, we can use. But from digital and analog sensor.
Cool. And which sensor should we be using for the group assignment? Any sensor that they have already that we connect to anything, literally.
I'm thinking of something which was really interesting, but maybe it's in the communication protocol. Ah.
Never mind, okay.
I have to ask Oscar. El I2c es un transistor analógico a digital y lo utilizaba para pasar de eso a de cómo hago, porque eso es analógico y el resto no puede leer. Entonces tienes que pasarlo a digital. Eso. Y que ¿cómo comunican entre ellos? Y ahí no sé vale. Entonces, para hacer una valdría como leer eso analógico, todo el mensaje que vaya a LCC, y después analizar el IOC para ver lo que está pasando. Sí, entonces en el working no tienes que hacer el editor de datos, tienes que hacer otras cosas. No, es decir, para eso. Ah, sí, porque eso leer lo que sale del IOC de 3.8. Sí, sí, pero hay que hacer analógico y digital. Sí, lo único que al final es, al final de ahí no es identificar como el protocolo, es identificar como
Okay. So let's go back and let's do a small stretch about this. I don't want, honestly, this part is going to be, or I could be like 5 hours talking about this, but I'm going to like keep it very simple. So the main purpose of this part is to talk about how can we make use of data or make use of the sensors in a smart way by using the data not only just to gather it or store it, but to analyze it using different techniques that can give us from good or bad sensors meaningful insights. That is the whole purpose of signal processing, and in this particular case, digital signal processing, which basically what we want to do is get some sort of signal and extract the information that that signal has. And that can be in many things. Can be whether a signal is higher than a threshold or lower than a threshold, or it has peaks, or it has a certain frequency, or whatever. Applications for this, you can imagine that is like as simple as I want to turn on something whenever the signal goes over a value, or I want to count how many peaks a signal has because I'm monitoring the heart of the patient. Okay, so at the end, this is something that I'm very motivated about, because I think that it's a good way to make use of simple hardware setups that might not be very expensive, but that can give you a lot of data if you analyze the data properly. For instance, what we do with those sensors. Those are less than 100 euros and are competing with hundreds of thousands of euros, not at the same accuracy, but you can put 5 of them and still be very low cost and get good information that the others one can give you. And somehow democratizes a little bit the game, and doesn't mean that you need a lot of money to monitor things. You, with small things and a little bit of extra that is not that expensive, you can get good results. Yeah. So that is why I am very keen on this part. And also I encourage you to not just stay on the, I read something, but I also analyze what it gives me. And I try to automatize that so that I don't have to do this process manually. I can extract information better, filter signals, or sorry, extract information better or communicate it better at some point. Okay. So first thing to know is that this applies for expensive and not so expensive sensors, meaning that there's no perfect sensor, and all sensors need some sort of digital processing. And you, for instance, know this very well. All sensors, no matter if they cost 5,000 euros or €1, need something. Actually, part of the 5,000 euros is the processing that they have. Yeah, how much filtering have you put in the hardware? How much analysis does the sensor unit actually does for you and gives you something, etc. So I think, well, important first point is that nothing is going to be perfect. No sensor is going to give you perfect data. And this, for me, is a must. It's not something that, oh, maybe I don't know. You should do this, and it will bring a step further, whatever you do in the projects, okay? So something, first example, the simplest one, we want to detect when a signal goes over a certain value, and we want to act upon it. So simple, you know, there's nothing very complex about it. You just have an if. Whenever the value that I'm reading is over a threshold, I do something. That can be turn on the lights because it's too dark, or turn on the heat or the fans or whatever. This is obviously so simple that it hurts, but it's not good, especially with good systems, or sorry, real systems that normally tend to oscillate. So see, when you read a sensor, a temperature sensor, or whatever, they don't normally stay at a constant value. They tend to vary and oscillate a little bit. That means that there's some noise on top of the sensor. If you just apply this, imagine that you are, for instance, using that to turn on these lights based on how much light it is. At some point in the day, there might be that your sensor is located in a point that there's a little bit of light and then not, a little bit and then not. And the lights are like click, 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 click all the time. Or in the evening, the lights are closing and it's just on the limit of the value that we set. And maybe the sensor sometimes gives us a higher value because, or there's a bird buzzing or whatever, and then the lights are ping, 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 ping all the time. If that's with a heater, or that is with a motor, or that is with a machine, then things get worse because an LED doesn't matter. But the heating machine, big motor, this machine, a 3D printer, etc. All these systems have prevention for that. Yesterday, for instance, one print failed because the temperature sensor was wrong and said and was oscillating between 180 and 250 and giving just random values between that. And the printer has a fail-safe that if that happens, I stop, I don't print because I don't know the temperature, the real temperature, right? So in that sort of, yeah. Ah, sorry, I thought you.
Oh, no.
So how do you make a decision, or how do you take a decision when you have a signal that is oscillating a little bit? And this is the concept of hysteresis. So let me, where is it? Here. So imagine that we have a signal that is not so stable. That goes something like this. If we only had a threshold, this is the threshold of the normal threshold of our signal. Here, we will turn it on because we're crossing to the other side. Here, we will turn it off. And here, we will turn it on again. In this short period of time, we will have done that 3 times. But what happens when we apply an hysteresis? The idea of the hysteresis is that we have 2 thresholds in one, but each threshold has a rise and fall component. So for me to turn on or to decide that my signal has crossed the value, I have to go above this value here. Okay, so whenever I cross here, I turn on, meaning that in this point, my system would be on. When do I turn off? Sorry. Actually, let me start over. Yeah. Let me start over. Actually, is more. I hate this thing. It's the opposite. So my signal goes like this exactly. So actually the threshold is this one. Sorry, it's this one here. So I turn on here, off here, on here. Where do I turn on? When I cross here.
And what happens between the...
In between here, since I'm going that way, nothing happens.
Okay.
And when I go back here, nothing happens until I get here. Okay, let's see it more. Actually, this is, I don't know why I put this graph. Let me do it in here. So imagine that, I'm sorry for this. Imagine that this is my graph. This is my temperature. And this is my threshold. Okay, here I turn on, off, and I turn on. And then I turn off again, right? If this signal is oscillating more, like here, then it's on, off, on, off, on, off. Now, if I have an hysteresis, I divide this threshold in two. And basically I say, if I cross, for me to turn it on, I have to be off and cross this value. So I turn it on here. For me to turn it off, I don't wait. I don't do it in here. I do it in here because I have to be on and cross this value. Yeah?
So the thermostats work.
Exactly. So if I have a signal that is something like this, in this case, if I only have a threshold here and here and here and here, I will be turning on off. But imagine that I came from here and I stay oscillating here for whatever reason, I get here. So I only turn on in this point. And then I don't turn it off again, right immediately. I have to go down to this value and I don't turn it off at all.
So technically it's not off. Like
Exactly. So
okay.
the signal would be like this, the resulting signal, instead of this.
Technically, you give a margin. That's it.
Exactly.
And the low
That's the only thing. And this is what we call hysteresis. Okay. How do you implement that? It's also very simple, just with an if loop, with an if statement. And
but then what's the difference between a threshold and a hysteresis?
A threshold is an hysteresis with the high and low the same.
Oh, okay.
Yeah.
Okay.
So in this case, it's the same. I read if I am over the threshold plus the width of the hysteresis. Oh, why? Why does that happen? But I was sharing, no?
Yeah, before, yeah.
So if I'm over the hysteresis divided by 2, then I do something. Otherwise, until I don't go below the threshold minus the hysteresis by 2. So what we drew, this one minus hysteresis or plus hysteresis, but the width of what we call hysteresis is the width of the margin. Then I do accordingly. And this already makes a massive difference into stabilizing systems. And obviously it's the way to go instead of just a simple threshold. Now, all signals, so no signal is going to be clean, no signal is going to be perfect, there's going to be noise. The cheaper the sensor, most likely or more likely, more noise there's going to be. The environment also affects the power that you have. If it's a power supply that is noisy, it will also affect. If there's a computer nearby with interferences, might also affect, etc., etc. Things that you have to do. First, hardware. Solve hardware problems if there's any noise from the hardware. But if there's the hardware. If, for instance, your sensor is next to a Wi-Fi antenna, very likely it's going to pick up something from the antenna. So away, or Faraday channels. But if you cannot solve it by hardware, then you have to filter the signal. Filtering the signal means removing noise, basically. And noise is any amount of unwanted and normally random affectations that a signal has. And that is on top of the signal, and that masks or hides the real signal that we have. So filtering, sometimes also people call it smoothing or rolling averages, is basically a process to remove noise from the signal. And the idea behind it is that what we're going to do is let me do annotations again. So what we're going to do is for our very noisy signal, the simplest version of our filter is going to be just taking a window, a certain amount of values, and we take each of them and we calculate the average. And then if, for instance, we have an agreement and we say, I calculate the average and I put it in the middle. Then I move a little bit more and I go to the next window, let's say. So I roll the average to the side. And then I take the average of these points here. I do the same and it falls in here. And then I do the same and it falls in here. And then I do the same and it falls in here. So, and then I join all of those in average, and my signal is going to be much smoother because basically these oscillations on average, they cancel each other. Okay. This is the idea of rolling average for obvious reasons, or
you do that through a code. No?
You do this through code. Yeah.
Give me the average of every, like, it's like.
Exactly.
Yeah.
Yeah. So you could do this by hardware using, for instance, a capacitor. But again, if you take a hardware decision like that, you might be losing something from your signal as a, let's say, and we'll see that nothing is perfect. So you will, there's always a trade-off and you will lose something. What is that something? If you, what I always say is that if you filter too much, you lose information. Imagine that I took a window that is like this. Then I take this point, this point, this point, this point, I don't know, and then my signal is flat. So I lost all the information that I wanted. So there's always a trade-off. And if you do that by hardware as well, then you can end up with something that is not what you wanted. So normally it's better to do it by software.
By hardware, the capacitor is grounded voltage line of your sensor.
Yeah. But that is, I wouldn't do that. Yeah. I mean, probably the sensor manufacturer tells you the signal, the data signal, you can stabilize it with a capacitor.
And they give you the value?
Normally, yeah. Yeah. But it's not normally the case. Now, how do we do that in Arduino? It's, as you can imagine, we need to take a snapshot of the signal and we need to store that somewhere because we need to take the average of some values, right? So we create, let me copy this and put it in Sublime, which is a little bit faster or looks better. So we define an array, a vector that is just a list of values where we're going to store them. Okay, and we say how many values do we want? How big is the window? 10. So we keep that in an array or a list of values, and initially we make them all 0. So all the values are nothing. And then what we do is that whenever we take a reading, we put that reading in an index that is switching. So it's going from one to another. In this case, it would be something like, this is our array. Yeah. And first I read a value and I put it in here. I read a value and I put it in here. The next one, I put it in here. The next one, I put it in here. The next one, I put it in here. When I get to the end, I keep all of them and then I start here again. What do I do every time? I take all of them and I make the average, which means I sum all of them and then I divide by, in this case, 10. And that is the average of something, right?
Where's that written in the code? Sorry, I missed it.
Yeah. So in the code, it goes like, I read the value in here, and I put it in readings, real index. So in the index that I am gonna, this is like the pointer to where I'm storing the data, right? Then here, I keep track of how much the sum of all the values is, and I call it total. So I say total in the previous step was whatever. I add the new value and I subtract the old value, knowing that every time I am shifting to the left, so I put one more and I leave one behind.
Okay.
Yeah. So I take one, so I move, put one, leave one, and I remove the one before and I put the one next. So this is what we do here. We subtract the old one and we put the next one. After that, here, this is just increasing the index. So I go to the next, and if I am at the last one, then I go to 0. This is here. If we are at the end of the array, we wrap around and we go back. And here we say the average is the sum divided by all of them. And then I print the average. And in a recursive manner, the first 10 readings are gonna not be good because they have zeros. And I put 1 until I fill the whole thing. But that just takes like nothing. The rest is gonna be always the average of. Yeah. And you can, if you wanted, you could print this and readings. You print this one, which is what you read, and the average, and you can compare and plot them both. And you see what gives you the noisy signal and the clean signal, let's say. Yeah.
Do this just for data analysis, or we can do it for. So for example, instead of doing the hysteresis, we do like an average in order to control. So for example, for control the temperature, instead of having the 2 thresholds, you just can take like the 10 last values that you got to the average, and depending on that, switch on or switch off.
Yeah, actually, that is, I like that because here is not in here, but when I do this, I always do filter and hysteresis or threshold. Hysteresis. And for whatever reason, I call this filthy. So filter and hysteresis. And I always say that a filthy signal, you clean it with a filthy processing, which is filter and hysteresis. So you filter the signal, and then you do either a threshold or an hysteresis. And I always recommend to do an hysteresis. It's gonna remove headaches, always. Like even if you clean the signal that we did before, it might be that it still oscillates a little bit, and you don't want that on some machines or something that you're controlling. So maybe it's better, and always depends on the application, to always apply an hysteresis. Yeah, but normally filter it. Be careful with how much you filter. You might be filtering too much or too little, and then apply an hysteresis to avoid oscillations on the output. Yeah. So, okay, I'm just gonna mention some more things. They are a little bit like too much probably, and it's already a little bit late, but I just mentioned them so that if you want to dig deeper, they are in here, okay? Gradients, what if I wanted to know if a signal is going up or is going down? For instance, is the temperature increasing or is the temperature decreasing? is my battery level increasing or decreasing? I don't know. Imagine that you are controlling the temperature of the machine. Normally, you control temperatures and these things with something we call PID, which we will talk about a little bit more at the end of the course, which is a controller. But imagine that you wanted to do your own controller, and you said, I am heating up something, and I want to know if I am going super high, super fast, or not so fast, or if I'm going up or I'm going down for whatever reason. Then you can use this idea of gradient, which is nothing very complex. It's just taking the distance, the increase that you have of your signal versus the time that it takes from one point to another. So you just divide this value by this value. The bigger it is, exactly. So you divide opposite by this one. This is the sampling frequency, and this is how much increased, and you get the slope. The higher the value of the slope with respect to your signal, then it means the faster it's increasing. The closer to zero means that it's not increasing. If it goes below zero, then it means it's going down. And here you have the code for doing this. Super simple. Just take the difference, and you can, if you want to be purist, you can divide by the sampling frequency, but in principle, you don't need to do that, okay? Now, very last things. Here, I'm not gonna talk about this thing called convolution, but basically it's a way for you to do all of this that I talked about in a standard way. And it gives you like a framework, a mathematical framework to implement all these topics in, let's say, in the DSP way, which is on a very standard method that basically applies things applies things with what we call convolutional operation, which is a way of, imagine before we said we take 10 numbers, we sum them, all of them, and then we divide it by the number of numbers that we have, or how many numbers we have. But what if we multiplied all of those numbers by 1 divided by the numbers, and then all those sum them? It's the same operation, right? What if we said, I divide in the middle, I divide by the number of items that I have times 2, and on the extremes, I divide by 10, and I have something that is more like this. Instead of all from the same factor, different. So that changes a little bit the shape of our filter, but we always sum them at the end, and we put them in our signal.
Can you repeat the last part?
The different formats. So here, it's really like not so important, but if you are motivated, don't worry. Yeah. Yeah. I think actually there is this one. Well, I took this one. I don't know if it's the same, but basically you take this signal. This is your window. Sorry, this is the actual signal, and this is your window. And the yellow part is the area between them, and this one is, let's say, the multiplication element by element of each of them, and then the sum. So at the beginning is 0, it increases, and then it goes down. The idea is that you take one signal.
Just because I don't understand, that's fine. The idea is that what is this used for?
Yes, because this is your signal, right? This one, sorry, this is not very good, but imagine that this is your signal in here with the different buckets, pam, 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 pam. And then it can be anything. It can be 1 divided by the number of samples. And then we have the average, but it could be something else. And depending on what it is, we can do very fancy things. For instance, we can take the average. We can take a different type of average, but it's a little bit nicer, like it doesn't affect the same way the old things versus the new things. Or we, for instance, can detect peaks. For instance, if you imagine that you have a signal that is like this, and that you have a filter that is this. And I do the convolution operation between both. And I say, okay, I do the convolution. This is going to be navigating through here. And I get an output signal. So here is going to be 0. Here is going to be a little value. Here is going to be like this. And then it's going to be the opposite, right? What if I do this again on this one? So I'm going to get something like this time. And if I do it again, something like this. And it narrows down, and then I say, okay, I apply a threshold. What is the peak? Here.
Okay.
Because I go here, boom. This is my peak. I detected a peak. Okay. I detected where is the top of the signal in an electrocardiogram machine, for instance. Yeah. Yeah. What if you want to detect if this is a rising edge or not, if the signal is going up or is going down, and I want to detect that. For instance, I do, instead of this one, I do something like this. Positive, negative. I get here, this is 0 times something very large, but negative. So the value here, let me erase a little.
So that could be just to single down a specific value in case you want to find something.
Exactly. So I get here, I have all zeros, negative value. Then I go to the next, positive, negative. So they cancel out. Go here, the other way, go here, boom. I detect a threshold, This is a falling edge. This is a rising edge. Because this is +1, this is -1, and they are navigating through. And here is the +1 times 0 is 0. But this one is here. So -1 times something very big is something very big but negative. When both are here, both are big. So 0 again, and then the opposite. So all of a sudden I have this signal, boom, and this other signal here. Yeah.
So many areas to detect pulse with the threshold because it was never the same height.
Yeah.
So it was not working. Then with the gradient, it detects several times.
Yeah. So things that you can do here. There's a couple of, I made this code a while back for implementing convolution, this generic operation in Arduino. And then you can just change the filter to detect different things. Rising edge, falling edge, peaks, etc. And the function is the same. You just change the filter and it gives you whenever there's something on.
And
okay.
If you want to give, if we can give a practical example of this being used.
For instance, I had students in the robotics detecting, they made a project that was like an exoskeleton to assist on construction. So you have one person that knows how to do something, and then someone that is learning, or that has problems in their arms or whatever. So this one is moving, captures the position, how much the muscles are flexing, if they are up and down, if they are rising, falling, etc. And the other person, the other one helps the person do the same movement, but only helps. It doesn't force, it just helps. So they put EMGs, so to detect muscle pressure, accelerometers, and flex sensors as well. And in each of them, they, for instance, in the EMG, for you to see if the muscle is flexing or not, you have a signal that gives you that you have to detect the peak of the signal. Then they detect the peak, they can know how much the muscle is flexing because they calibrate it. They say, don't flex, then flex. They say, okay, you're flexing 50%. Then they send that 50% flex on this. Then flex 50% on this. And they are able to assist on someone moving and the other person doing the same. And for this, you need a lot of digital processing because otherwise the other person is like, yeah, you know.
Yeah.
Yeah. So this part I think is normally a little bit unused in academy because we touch a lot of hardware, but I think it's very powerful as well. And it's important if you want to dig deep that you make use here. I like it a lot, and some other people like Victor, they also are into like trying to get insights from the data from, let's say, not so expensive things. And I encourage you to try with anything. It can be a purposeful sensor or it can be anything else that is not a sensor, but you can turn something into a sensor by maybe putting a little bit of effort into the data analysis part. Yeah.
One question. I was wondering for my final project, I'm measuring current, like so oscillation, and I know that the frequency will be 50 hertz, and it's like second order Ordino. So can I use that to measure less information and then reapproximate the equation?
I think so. Yeah.
Do you have an example? Because there is two things. There is for the measurements, speed that I can maybe use, and also for data compression.
Okay.
And those two information so I feel there is something, but practically I'm a bit lost on how to use that.
So, well, at least you need to measure using like what we said before, the Mqtt theorem, twice as much of the frequency. That is unquestionable.
Okay. Even knowing the frequency in the shape?
I think so, because at the end what you want is to detect when it's crossing zero, right?
No,
or no?
I'm interested in the peak to peak.
You just want the amplitude.
Yeah.
Maybe,
I don't know.
I'm not sure.
Variable, if you need, how many points you need.
Well, the second order, you need at least 3 variables.
Okay.
And that
so maybe it corresponds to the
same. Yeah. Yeah. I'm not sure, but we can look into it. Also, I recommend if you want it's not in Arduino, but in SciPy. I don't know if you used it, but they have very good documentation.
Okay.
Is scientific measurements in Python, and they have a package called Field or Signal, I think. Documentation. It's just a Python package, and here there's quite a bit of information about each of these things. Maybe something in signal processing or Fourier transform. I will look into that and try to get some insights from there. No, just.
And can we mix Python and C? I mean, in Arduino, or how does this work?
No, in Arduino it's going to be not easy. Well, you cannot do it unless they're using MicroPython, but I don't think that they have ported SciPy to MicroPython. What I would do if you need this type of setup is either keep it very simple in Arduino, or if you want to go full-fledged, go with a Pi or something a little bit more powerful and try to implement something like this. An FFT, for instance, is going to be impossible to, because that is like insane implementation. But there's implementations of FFT algorithms in Arduino as well. So, but it's a little deep,
yeah,
I would say.
Find it so complicated.
No, I don't think so. But one setup could be Arduino and a small Pi 0, for instance, or your Arduino and a small Pi 0.
Or the SP32.
Yeah.
Can do this kind of thing, no?
Yeah, but you wouldn't have SciPy, for instance. You would have to use something else. But there's a lot of mathematical stuff in Arduino already. Probably not so like this, but I think this is interesting only for detecting, for reading, and learning a little bit about signals and things like that, but not so much as into implement it actually for your project. But yeah, so you can see that like there's like even papers and a lot of, it's very well documented. Yeah, I'm gonna run out of battery. So I'm gonna close at least the session. Guys, I'm gonna close running out of battery. Do you have any questions at home? Maybe. Let's see.
Nope.
No?
Nope.
Okay, so then see you around, and thank you. Yeah.
Goodbye. Thank you. Goodbye.